In a massive AI setup, where jobs run on hundreds or sometimes even thousands of GPUs, keeping everything efficient is the key. That is where traffic load balancing, congestion management, and choosing the right topology for your data center are the essential steps to keep traffic running smoothly. When AI training kicks into higher gear, the need for high-performance lossless networking becomes absolutely critical. To make this happen, admins need to carefully fine-tune the right mix of hardware, software, and configurations, ensuring everything is built to handle the specific demand of AI, for example, training or inferencing. Here's where things get more exciting. When it comes to network topology, nothing beats the class design, or in other words, the span and leaf topology for AI workloads. And why? One of the reasons why this class design is so powerful that it's designed with a non-blocking mechanism, non-blocking fabric, which means every host gets full speed access to any other host without any drops, with zero slowdowns. It delivers deterministic performance, ensuring low and consistent latency even when the network is flooded with traffic. But having a killer topology is just one piece of the puzzle. The real game changer is how you manage traffic flow through the network. Take ECMP as an example, equal cost multipathing. Ideally, ECMP balances traffic evenly across all available links, giving you maximum bandwidth. But here's the catch. ECMP's hashing function does not consider link load. This means you could end up with traffic piling onto a single uplink, slashing your bandwidth in half and creating bottlenecks. That's not it. Also worth mentioning that out-of-order packet delivery is not acceptable for RoCE technology. Okay, well, this is where more packets are dropped if they were out of order, if you rely on InfiniBand switches. Oh, so what do? This is where Ethernet steps in with a bunch of different advanced techniques that has some kind of intelligence to it. They use techniques such as Ultra Ethernet and Scheduled Ethernet that will spray and reorder your packets. So wait a sec, what did you just say? Spray? Yes, spray and reorder. These techniques are actually very intelligent. What do? They spread your packets across all the available links. Okay, that's what ECMP does. But wait for it. Based on the actual traffic load. And don't worry, packets are perfectly reassembled. This is where the word reorder. Packets are reassembled at the destination again. The result, blazing fast performance that keeps your network running smoothly no matter how intense the traffic gets. You get these features with Cisco Nexus 9000 series switches that support UEC technologies. This stands for Ultra Ethernet Consortium. I'm not trying to sell you the Nexus 9K switches. However, they really have those different techniques. The Cisco Nexus 9Ks, they're considered DSF switches. What does it stand for? Disaggregated Scheduled Fabric. And what's that? I'm going to explain this in a bit. The DSF switches have some kind of load balancing technique, but to begin with, what's a DSF switch? Okay, well, this is a disaggregated schedule fabric architecture used in AI and machine learning networks, which ensures efficient low latency data transmission by dynamically balancing traffic across the links. What's new? DSF devices, they take traffic balancing to a whole new level by intelligently reordering packets across all available links, ensuring every flow is treated fairly. Here's the cool part. The ingress leaf switches, they do the packet reordering on the way in. And then the egress switch puts everything back in the right order before it reaches the destination. Since this approach doesn't rely on traditional hashing, it avoids any flow collisions thanks to Cisco Silicon One, making traffic management smoother and, again, more efficient. Worth mentioning that the Cisco Nexus 9000 series switches are built based on the latest ASIC technology. This ASIC is the cutting edge technology with software programmable chips that support 4 different Ethernet modes, each designed for specific performance needs. Starting with standard Ethernet, which is, your standard mode using stateless ECMP load balancing, but it's not the most efficient option. So this is where enhanced Ethernet comes into play. This is the smarter mode, taking into account how busy the links are when balancing your traffic. It keeps track of the network state and only balances traffic when the flows are idle. Then we have the Ultra Ethernet. This goes a step further by using adaptive packet spraying controlled by endpoints for even better fabric utilization. And then last but not least, the scheduled Ethernet. This is, I can call it the top notch. This is the best performance. It uses the spray and reorder method, which ensures optimal load balancing. It avoids common issues like head-off line, HOL. Head-off line blocking, where a single packet holds up the other packets and prevents congestion, which happens when multiple sources overwhelm one output. So be careful. Well, I'm already careful because the scheduled Ethernet is going to take care of that flow for me. There are other techniques that you can take into consideration when designing your AI workload, when you design your data center to support the AI workload. Why? Because you need 0 packet loss and you need lower latency and less delays. So what does it mean? It means that I can configure some kind of advanced kind of quality of service mechanisms, things like ECN and PFC, explicit congestion notification, and priority flow control. What do? Well, first off, the ECN. Your ECN devices, your ECN switches, your Nexus 9000 series switches, they need to support these kind of techniques, which they do. So what's going to happen? In case they start sensing congestion into your network, they're going to start sending some kind of packets. Those packets are called the ECN packets. The ECN packets or the CNP packets, they're going to start negotiating slowness in the network. In other words, one switch, if it gets congested, it's going to shout to the rest of the other switches, hey guys, guess what? There is some kind of congestion happening. Please slow down a little bit. Reduce your speed of sending your packets so that I don't end up dropping those packets. ECN, well, every single source, including the switches along the path and the original sender, they're going to slow down their sending rate. And on the other hand, what if it still keeps having congestion? What if that switch was still suffering from congestion? What's going to happen? It's going to take it up a step further, and it's going to start sending what we call the PFC packets, trying to alarm everybody. Oh, well, slowing down is not enough. Guess what? We need to pause priority flow control. We need to pause sending traffic because guess what? It's still being congested. My interfaces are congested, so you might as well, Mr. Sender, not slow down, but pause sending until everything cools down, and then we can retransmit or start sending back again instead of losing your traffic, instead of dropping traffic. Lots of cool techniques here within your AI-enabled data center that you need to follow to ensure a lossless fabric. Summary time. Spinal leaf topology. This ensures non-blocking low latency performance for your AI workloads. Poor ECMP hashing can cause congestion by uneven load balancing, reducing your bandwidth. So you have techniques like UAC, scheduled Ethernet to optimize traffic flow, ensuring smooth performance on Cisco Nexus 9000 series switches. DSF load balancing dynamically balances traffic, avoiding collisions and boosting efficiency with Cisco Silicon One technology. I hope that this was informative, and I'd like to thank you for viewing.